Ladies and gentlemen, now we look at lecture 8 on module 3, which is now covering fire and explosion modeling. In this lecture we will discuss you step by step how to draw a flammability diagram. Before we do that, let us quickly revise what are the essential characteristics of material with respect to fire and explosion modeling. We have understood what is an auto ignition temperature, what is a flash point, what are flammability limits for a given material or a mixture, and what we understand by limiting oxygen concentration. We have also understood the flammability limits behavior, which is temperature dependent and pressure dependent. We have seen that as temperature increases, upper flammable limit increases, whereas lower flammability limit decreases. On the other hand, we can say very easily that the flammability range keeps on increasing with increase in temperature. On the other hand, look at the pressure dependency. We have already shown that the upper flammability level increases as pressure increases, but the pressure has less influence on the lower flammability limits. Now ladies and gentlemen, let us see how to actually draw a flammability diagram. The following steps are very important. Draw the lower flammable limit and upper flammable limit on the air line. We have already seen in the last slide a flammability diagram basically has 3 arms of a triangle. One arm contains the fuel, one arm contains oxygen, other arm contains nitrogen. So they have been specifically marked as 0, 100, 0, 100 and 0, 100 in a specific order. Now for a given fuel, you understand to know the lower flammable limit and upper flammable limit. Mark these limits on the airline. I think you appreciate if I say airline because you understand what I mean by an airline. Airline is nothing but the line joining the apex of oxygen arm to about 79% on the nitrogen or 80% nitrogen arm. There is a simple line which we call as an airline. So mark LFL and UFL on the airline, locate the stoichiometric point on the oxygen axis. This can be obtained from the chemical reaction or the combustion reaction of the fuel. Draw the stoichiometric line from this point to apex of the nitrogen arm, locate the limiting oxygen content of the oxygen axis and draw line parallel to the fuel axis until this intersects the stoichiometric line. Mark this point of intersection. Now draw LFL and UFL in pure oxygen if they are known for a specific fuel which you are considering for the problem. Basically it is nothing but the percentage of fuel in pure oxygen. If you know that, try to mark them on the pure oxygen arm. Connect the points to get the flammability diagram. Now let us see interestingly an animation how to draw the flammability diagram. Here is animation to draw the flammability diagram. So you draw the nitrogen arm, you draw the fuel arm, you draw the oxygen arm, you draw the air line, you locate the stoichiometric point, draw the stoichiometric line, locate the UFL and LFL on the fuel arm, mark LOC and draw the line and try to find what is the concentration of fuel on pure arm, join these points to get the boundary of the flammability diagram. So this region is what we call as flammable region. Once again let us try to understand how to draw this flammability diagram, but in reverse order. Let us say you have drawn the diagram, I am just explaining in reverse order just to know how you have drawn. Once again let us try to understand how to draw this flammability diagram, but in reverse order. Let us say you have drawn the diagram, I am just explaining in reverse order just to know how you have drawn the diagram. If you want to draw the flammability diagram for a specific mixture, let us say for example methane, identify the flammability characteristics of methane which is available in the standard literature. The flammability limit of the fuel in air LFL and UFL are given in the literature. The flammability limit in pure oxygen for the mixture is also available in the literature, and of course the limiting oxygen concentration is taken as 12% of oxygen. So this becomes my combustion reaction for the chemical which I am considering, or for the fuel which I am considering. Comparing this chemical combustion reaction, which will be, this is general expression, this is a specific expression for my specific example of CH4. Comparing these two equations, I can easily say my Z is basically 2. Now for Z equal to 2, the stoichiometric point can be computed from a simple expression like this, which gives me 66.7% of oxygen. Now once I get this, for all the LFL and UFL values in pure oxygen and in air, I already know for methane. Let us try to draw the flammability diagram again for this given example. I draw the nitrogen arm, I draw the methane arm now, I draw the oxygen arm, I locate the air line, I locate the stoichiometric line, I locate LFL and UFL on the fuel arm, I also locate the LOC, I locate the pure oxygen arm of the fuel, join the boundary and get the flammability region. This is how I draw my flammability diagram for methane. Let us, for more understanding, let us see this diagram in a finished format and look at the reverse steps of this diagram. I have already drawn the diagram, now I am seeing how I have drawn this diagram for better understanding. Ladies and gentlemen, you must have now understood how to draw the flammability diagram for a given fuel mixture. This is the completed diagram for a specific fuel. We already know this is the fuel arm 0 to 100, this is the oxygen arm 0 to 100, nitrogen arm 0 to 100. The numbering of this has a specific order, it is anti-clockwise 0 100, 0 100, 0 100, nitrogen arm, fuel arm and oxygen arm. When you know this, try to draw what we call as air line, which is 79% of nitrogen, draw that with apex of the fuel or origin of oxygen and draw a line, call this as air line. Then for the fuel arm, you already know the LFL and UFL values in pure oxygen as well as on the fuel. Let it intersect the air line and get these points, get the intersection of the stoichiometric line with that of the LOC, get the nose of the curve, and this becomes flammability region in air, because this is my air zone. So this part basically is air zone, this part is basically the oxygen zone. So flammability zone for oxygen is this blue one, the flammability zone for air is the red one. So if you have the oxygen concentration reduced, then the flammability region can be highly reduced. When you look at the explosion models, there are some basic definitions which we have got to understand. Explosion is actually a rapid release of energy causing development of pressure or a shock wave. The energy may be pressure energy or a chemical energy. There are different types of industrial explosion which we will now describe one by one. The first one is what we call as confined vapor cloud explosion, CVCE. This is an explosion which could occur in a contained vessel or a building. This is essentially caused due to release of high pressure or a chemical energy. For example, I have a contained vessel, the pressure in the contained vessel is increasing and that could result in an explosion. This kind of explosion is what we generally call as confined vapor cloud explosion. The second type of explosion is simply called vapor cloud explosion. The confined part is removed from the definition. So this is an explosion caused by instantaneous burning of a vapor cloud which is formed in air due to release of a flammable chemical. So there is a flammable chemical which has been released in air that has resulted in a cloud which we call as a vapor cloud, and that explodes by some source of ignition. So, I have a cloud and this ignites, this is what I call as vapor cloud explosion. The third kind of explosion is what we call as BLEVE, which is expanded as boiling liquid expanding vapor explosion. Now, in this case the explosion is mainly caused due to instantaneous release of large amount of vapor through a narrow opening under pressurized condition. I have a contained vessel, I have an increase in pressure in the vessel, and there is a narrow opening through which the large amount of vapor is instantaneously released. That will result in a special kind of explosion what we call as a BLEVE. So, the pressure is increased in the vessel and there is a narrow opening through which it will get released, and that causes the explosion. This is what we call as BLEVE. The fourth kind of explosion is what we call as vented explosion. This is an explosion which is caused mainly due to high speed venting of chemicals. So, I have a chemical, this is released in the atmosphere at a very high rate, and that results in an explosion what we call as an vented explosion. You can see here that there is an instantaneous release of large amount of chemical from the vent. The next kind of explosion can also be caused due to the presence of dust. This is called as dust explosion. The explosion is resulted from a rapid combustion of fine solid particles. There are fine solid particles that gets combusted and that results in an explosion. So, this is what we call as dust explosion. The explosion characteristics are actually very difficult to characterize them. Explosion energy is actually dissipated in the form of a pressure wave, projectiles, thermal radiation and acoustic energy. In this context, it is very important to understand what do we define by a blast wave. Blast wave is actually a shock wave in an open air, generally followed by a strong wind. Basically, it is a shock wave in an open air which is generally followed by a very strong wind blowing. What do we understand by overpressure? If the pressure of an object results from an impacting shock wave, then we call that as an overpressure. Detonation is also called as an explosion in which reaction front moves at a speed greater than sound in that medium. On the other hand, the reaction wave is much greater than the speed of sound. So, sound is heard later, prior is the explosion. Such kind of explosions are specifically termed in literature as detonation. Sound is heard later, reaction comes first. There is another kind of explosion which is termed as deflagration in the literature. This is also a kind of explosion in which the reaction front moves at lesser speed than the sound in medium. On the other hand, the reaction wave is having a speed lesser than that of the speed of a sound wave. So, first sound is heard, then the reaction comes into play. This kind of explosion is what we call as deflagration. Now, let us quickly see how do we compare a deflagration with the detonation. In deflagration, the reaction front moves at a lesser speed than that of sound, whereas in detonation the reaction front moves at a greater speed than that of sound. Here in deflagration, the pressure wave moves away from the reaction front at the speed of sound, whereas in detonation the pressure wave is slightly ahead of reaction front, moving at the same speed practically. The pressure wave front resulting from a deflagration is characteristically wide. So, it is a very wide phenomena for a larger distance and with a maximum pressure much lower than the maximum pressure for a detonation. So, the maximum pressure what you get here is much lower than that of the maximum pressure what you get from a detonation. Whereas detonation, the pressure front produced by detonations and deflagrations are markedly different. The detonation produces a shock front with an abrupt pressure rise and the maximum pressure of greater than 10 atmospheric, and the total duration is very small, it may be practically 1 millisecond. So, detonation is an instantaneous process where the reaction front moves much faster than that of sound. So, you first see the explosion reaction, then hear the sound where a very small duration, whereas in deflagration you hear the sound first, then the explosion comes, and that is practically spread for a larger time duration. However, the pressure rise in detonation is much higher than compared to the pressure rise happening in the deflagration. Now, let us try to understand something called ignition energy. It is nothing but a minimum energy input required to initiate combustion for a given fuel or a mixture. Any fuel or a mixture requires a minimum amount of ignition energy which is to be given as an input to initiate the combustion process. Generally, all flammable materials have a minimum ignition energy requirement, and this MIE value depends on specific chemical or the mixture of the chemical. When it is a mixture, then the concentration of different components of the mixture, and of course on the operating temperature and pressure of the mixture. For different chemicals, for our understanding, I have already presented in a tabular form the MIE value in MJ: acetylene, benzene, butadiene, butane, hexane. The values are given for different chemical in terms of MIE values. Then let us try to understand what will be the percentage contribution for ignition source from different sources. So, if you take electric as an ignition source, generally the contribution for combustion or ignition is about 23%. When you look at smoking is about 18%. You look at friction, which develops heat, which is also causing ignition, that is about 10%. If you already have any overheated material present in the scenario or process, it may cost or it may contribute to 8%. If you have any hot surfaces, that may contribute to 7%, flames can contribute to 7%, sparks can contribute to 5%, and others put together can contribute to 22%. Thank you.